Okay, class. To start off, before I get into the slides, I want to motivate the material we're going into by building off of what we finished on in class. So remember in class we had rabbits and foxes, and this was the population in rabbits and fox units, like 1,000 rabbits, 200 foxes. And then if we multiply by this matrix once, that would tell us what the population would be the next year. So the task was to figure out the 15th year, and that was hard. Okay, so that's why I have hard right there. We found that if we were able to translate things into eigenvectors, then the multiplication became easy, because multiplying by this matrix, if we were multiplying an eigenvector, then it's just the same as multiplying by the vector by a constant. And so one way to represent that, we didn't go this far in class, but if this is the coordinates in the eigenvectors, so this tells me, so here, let's go to these coordinates. This is 1 unit of rabbits, and this is 2 units of foxes. Okay, easy for us to think about, rabbits and foxes, but hard for us to compute. Over here, if we are able to translate rabbits and foxes into coordinates of eigenvectors, so this is half of evect 1, which is 1, 0, and 2 of eigenvector 2, which is 1/4, 1. In one of the classes we used 1, 4 instead, but I'm going to stick with 1, 4, 1. These coordinates, this tells me the same spot. The 1/2, 2 tells me the same spot as 1, 2. I just have to get there a different way. I go 1/2 in this direction, 1, 0, and then 2 of the 1/4, 1 direction, and I end up in the same spot as going 1 in the standard basis, which is 1, 0, and 2 and 0, 1. I get the same spot. But if I can represent rabbits and foxes in this eigenbasis, these eigencoordinates, then the multiplication is easy, because I can multiply by a diagonal basis. Every time every year, no matter what my value is for this eigenvector, it's 1.5 farther. It's 1.5 times that the next year. And every year, no matter how many I start, it's 1.1 times that the next year. So I can just multiply, to do the 15th year, this is nice, it's a diagonal matrix, that's just 1.5 to the 15th, 1.1 to the 15th, and then I can multiply these in at the end, and I get where I'm at. The problem is, like here the computation is easy, but that's not rabbits and foxes. It's not rabbits and foxes. We want rabbits and foxes. So if we do this trick, we have to translate to rabbits and foxes, or start with rabbits and foxes, translate into this, into eigenvector coordinates, and then we have to translate back to rabbits and foxes. And it still can save us tons of time if we do that. But let's actually do the computation. So the way we went, so our eigenbasis was 1, 0, 1/4, 1, and we searched to find what can I do here that's the same as 1, 2 in rabbits and foxes. Okay, and we found, well, this one has to be 2, because that's the only way to get 2 there, and so using that, turns out this has to be 1/2. So this matrix here will go eigen coordinates to rabbits and foxes. Okay, if you give me the eigen coordinates, I multiply by this matrix, and I get rabbits and foxes. Great. How could we go back? What if we started with rabbits and foxes? Well, the inverse will take us the other way, right? If we have 1/2, 2, I can think about multiplying by the inverse on this side of both of those. Then, and I take 1, 1/4, 0, 1 inverse times 1, 2. Then this takes rabbits and foxes to a rabbits and fox coordinate to my eigenspace coordinates. So now, using what we have in here, we can start and end with rabbits and foxes, but we can do the easy computation. So I would like to have two. So this is what I'd like to do. I'd really still want to do this, but I want to rewrite it in a different way. So I'm going to rewrite it down here. 1.5 minus 0.1, 0, 1.1 to the 15th times 1, 2. Now, I still want to start with rabbits and foxes, 1, 2. But what I want to do is replace this, figure out what I need to do to get this. I want to start with rabbits and foxes, but I need to translate it into, by doing a 2 by 2 matrix, I want to translate it into an eigenbase coordinates. And then, so I want to go rabbits and foxes to eigenbase. And then once it's in the eigenbase, these two things will be an eigenbase. I can just multiply. I can do the computation very easily with that diagonal matrix. The problem is I'll still be in an eigenspace. All of this will still be eigencoordinates. So, because this just does eigen to eigen. It does, you give me the eigencoordinates of the, in year 1, I'll tell you what the eigencoordinates are year 15, but that's not easy to read for us. We want rabbits and fox coordinates. So what I want at the end is I want to have the rabbits and I need something, a 2 by 2 matrix that'll take my eigens back to rabbits and foxes. And the things that we need are up here. So you notice this is rabbits and foxes to eigens. So we could do 1, 1/4, 0, 1 inverse. We can, and this one, this is the matrix that goes eigen to eigen coordinates to rabbit and fox coordinates. So 1, 1/4, 0, 1. And now we are happy. We get both things because we can just start with any rabbits and foxes that we want, and then we can take any year that we want, but let's just stick with 15. So we can take any rabbits and foxes, put it in here, multiply by this matrix once, then take this power to the 15th, but that's easy. That's just 1.5 to the 15th, 0, 1.1 to the 15th. Right, that's easy to do, and then we'll translate it back with this one. So, and these two matrices together we already know is 1/2, 2, etc. So we can do this fairly easily if we have ways of translating back and forth. So this crazy computation here, we can rewrite as all of that. Now, that means that what we've done is we've rewritten, pull out another color, we've rewritten this matrix that's the same as these three matrices. So 1.5 minus 0.1, 0, 1.1, that is the same as 1, 1/4, 0, 1. 1.5, 0, 0, 1.1. And 1, oops, 1/4, 0, 1 inverse. So we have rewritten the matrix on the left with these three matrices on the right. So we can think about this as factoring down. We just factored down this matrix into into a product of three matrices. And this is nice because we get to see exactly what the eigenvalues are of that matrix, and we get to see exactly what the eigenvectors are for that matrix. And when it comes to computing, this is often a lot easier to use. So this is called the diagonalization. Diagonalization, I don't know how to spell that. I used to just write DIA when I was in grad school for diagonalizable or diagonalization. So this is a diagonalization, and we've already seen places where it helps us a lot. This structure turns out to be valuable even if this middle one doesn't turn out to be diagonal. So let me rewrite this as sorry, I'm just grabbing the book because I just wanted to use the same notation as the book here. So they use, okay, so they call the diagonalized matrix D, and they put P inverse P, and this is A. So that's A. This is our diagonal matrix D. And then we have this matrix that multiply the inverse on one side, the non-inverse on the other side, and this is the same. This is a really important structure. And sometimes there are other matrices, even if D isn't diagonal, if it's just another matrix that we'll call B, sometimes you can write matrices this way. And it's even if B isn't diagonalizable, it still shows an important relationship between A and B, and this is called similarity. So A is similar to B, and vice versa. Turns out if A is similar to B, B is similar to A. And the notation is A, and then you do the squiggle to B in the same way that two geometric figures are similar. It's the same thing, like triangle 1 is similar to triangle 2. So so the big use of diagonalization is taking things that are hard to compute or sometimes even hard to think about and putting them into this factored structure where we can better understand what's going on or better compute with them. Similar thing with similar matrices. Sometimes well, let's dive into the slides. So the book, the chapter and slides start with similar matrices. I think it's more appropriate to start with diagonalizable matrices. So this is near the end, and this is actually where I want to start. Let's talk about how we're going to diagonalize the following matrix, because this actually follows what we did back here with this one. How did we do it? Well, we need to define eigenvalues. We need to define the eigenvalues, and we need to define eigenvectors, and we use those in a special way to diagonalize. So that's where we're going to start, is we're going to do the diagonal. We're going to start by finding the eigenvalues and eigenvectors. So we know how to do that now. Subtract lambda, find the characteristic polynomial, factor down, solve for lambda 1 and lambda 2. We've got them, minus 1 and 2. And then if you subtract a minus 1 from the diagonal, then we end up with this matrix. And we row reduce. We get that y is a free variable. This is our basis vector for lambda equals a minus 1. So we have an algebraic multiplicity and a geometric multiplicity of 1. And for lambda 2 equals 2, subtract it from the diagonal, row reduce. y is a free variable again, and we get this 2, 1 as a basis vector. And so what you do is you take our two eigenvectors. So they were 2, 1 and 1, 1. So you write them down. And order is important here. So 1, 1 came from our lambda equals minus 1. So right when we subtracted minus 1, we got the 1, 1 eigenvector. So if I put that first, the 1, 1 vector first, I need to put the lambda, the eigenvalue it's associated with first in the diagonal matrix. And then our second one was 2, 1, and it corresponded with 2, so I put it second. So order matters. That gives me these two vectors. I'm sorry, these two matrices, and we're most of the way there. And the last thing we do is we take this matrix and find the inverse and put it at the end. This is the same structure that we did with the rabbits and foxes, because this will take a matrix with the standard basis, and it will translate it into coordinates with the eigenbasis, and then it does this transformation to it in the eigenbasis, and then this translates it back to the standard basis. Or another, we can do it with another basis too, and that's the same thing as multiplying by that. So you can multiply it out and check for yourself, but that'll be the same thing. So that's a simple example. And here is the more complex example. Oops, actually, let's go back to diagonalizing this one. So you start by finding, this is a 3 by 3, but the process is the same. You start by finding your eigenvalues. So you subtract from lambda, find the determinant, do the factoring down, find the solutions, and you get lambda 1 and lambda 2 equals 1. So an algebraic multiplicity of 2. Here the algebraic multiplicity is 1. Then you have to do the work of finding the eigenbasis for each of these. For lambda equals 1, it's these two bases. So geometric multiplicity 2. And for lambda equals 3, we just get one basis vector. So the geometric multiplicity is 1. And notice they're the same. So the geometric multiplicity for lambda equals 1 is the same as the algebraic multiplicity and such. So what do we do? Okay, we have 3 basis vectors. We have 3 eigenvalues because we have 2 1s. So we construct the matrix P from the eigenvectors. So if we go back, you'll see that we have 1, 1, 0, 0, 0, 1. Those are the first two, 1, 1, 0, 0, 0, 1. And then we had a minus 1, a minus 2 thirds, and 1. And you can come here, you get a minus 1, a minus 2 thirds, 1. There's P. Then you can write down the diagonal matrix. It has the eigenvalues, and the order matters, right? 1 is the eigenvalue for that vector, 1 is the eigenvalue for that vector, and 3 is the eigenvalue for that vector. So the order matters. And then the inverse, P inverse, we write over here, and we've now factored down that initial 3 by 3 matrix into the product of an inverse matrix, a diagonal matrix, and then the inverse of the first matrix. So if you do it that way, so P inverse, diagonal, P. And so yeah, here we have we can easily see the eigenvectors, and we can easily see the eigenvalues. So I'm kind of going backwards, so let's go up to so here the book just says, hey, these are similar matrices, but now we start to understand like why you might want to do something like this. because if A is diagonal, then that's really, really nice. So if you can connect A and B with a matrix P and P inverse in this way, it doesn't matter if you do P here, you can do P here or P inverse. That's just fine. You've still found matrices that have this property. If A and B are similar n by n matrices, then they have the same characteristic polynomial and the same eigenvalues with multiplicity. So if there's two ones and then if the algebraic multiplicity is 2 for 1, then in A, then it would be the same for B. It would have eigenvalues with a multiplicity 2. Eigenvalue of 1 with multiplicity 2. You guys already know how to do this, how to find the characteristic. This just shows that you get the same characteristic polynomial, so A is similar to itself. Blah. So, oops, did I skip something? Yeah. So just because the two matrices have the same characteristic polynomial does not imply they're similar. If they're similar, then they have the same characteristic polynomial, but not necessarily the other way around, like going back. Similarity is not the same as row equivalence, so row operations may change the eigenvalues, so be careful. It's diagonalizable if it's similar to a diagonalizable matrix. So we already talked a little bit about that. And the diagonal matrix, it'll have to have down the diagonal the eigenvalues. So here they just showed to verify that this actually works. So A is diagonalizable because it's similar to a diagonalizable matrix, so you can multiply it through. And this gives us, this is where we started with an example kind of like this. If it's diagonalizable, then you can easily find powers, because when you start writing down the powers together, the P inverse and the P will cancel out, and you just get the D to the inside one to that power. So easy to do the powers. And so now the question is, when is it diagonalizable? Can you always do this? So big theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So the big key is n. All eigenvectors for a matrix are linearly independent, but the trick is getting n of them. So sometimes you don't end up with n eigenvectors. Sometimes you might have less. You can't have more, but sometimes you can have less. So moreover, A equals PD P inverse with D a diagonal matrix if and only if the columns of P are n linearly independent eigenvectors of A. So the key here is, again, n. The linearly independence actually already comes from, like, eigenvectors can't be, all the eigenvectors for a matrix are linearly independent, but the trick is getting n of them. The diagonal entries of D will be the eigenvalues of A in the same order as the eigenvector columns of P. We already saw that. And how are we going to know if we have n things? N, we're building up to that. This does the process, and we already went through and how to do those things. We did that one. And if you try to diagonalize this matrix, you'll end up with problems. So the issue is all the multiplicities are 1. Sorry. The eigenvalues are all 1 with multiplicity of an algebraic multiplicity of 3. But when you subtract 1 from the diagonals, you get that y and z are free variables, and you only get a line in the eigenspace. You could just only get one eigenvector. Well, how can you build your P? Because this is a 3 by 3 matrix. We need to have another 3 by 3 with the diagonal In our case, they'd all be 1s, because those are our eigenvalues, and with P inverse. But we need to have, these all need to be eigenvectors, all 3 of these. But we only have 1. What are we going to do? Well, that's the problem. We can't do anything. We cannot diagonalize this matrix. It looks simple, but we cannot do it. There's a theorem. As long as you have 3 distinct eigenvalues, you're good. So if you have an algebraic multiplicity that's more than 1, it still might be able to be diagonalizable, but that's also where you start having problems. If you know all of your algebraic multiplicities are 1, then you know enough for it to be diagonalizable. It doesn't work the other way around. Yeah, so here we've got an algebraic multiplicity of 2 with our eigenvalue 1, but it was still diagonalizable. That was fine. So the big thing was this. So if the geometric multiplicity of lambda is less than or equal to it, oh, we already know. So sorry, it always is less than it. But oh, sorry, where is that thing? Oh, here we go. If the geometric multiplicity of lambda is less than the algebraic multiplicity, then it cannot be diagonalizable. So the algebraic multiplicity and the geometric multiplicity have to be the same for all lambdas. So the geometric multiplicity can't be more. It's always going to be less than the algebraic multiplicity. A is diagonalizable if and only if the geometric multiplicities add up to n. So so this is where the problem comes in, because the geometric multiplicity could be less than the algebraic multiplicity. Algebraic multiplicities always add up to n, but the geometric multiplicity, you could be short and not have enough eigenvectors. If A is diagonalizable, then combining bases for each eigenspace gives a basis for all of Rn. So it's another part of the theorem. Okay, I think it's enough for you guys to go on. We will see you guys in a couple days. Thanks.